So first off, thank you everybody for coming. Thank you everybody else for your talks. They've all been great, and I'll attempt to end this off on a decent note. So my name is Sam Jenkins. I'm a rising senior at Elon University in North Carolina. I've been working this summer in the Birch Lab, exploring new phases of matter through superconductivity. Before I jump into it, I'll give you a brief outline of what my presentation is going to be about. I'll start off with an introduction to the project, the motivation for it, why we do what we do, and the applications of it. So this is a picture of a chip in a quantum computer, and quantum computing is one of the potential applications of our work, and I'll get into that a little bit more. I'll also give you a brief introduction into superconductivity, why we use superconductors, some properties that superconductors exhibit, one of which is zero electrical resistance, which is what this graph is of. So when you cool a superconductor down at some critical temperature, it starts to show zero electrical resistance. And for a normal conductor, even if you cool it down to absolute zero, it will show some finite resistance. And I'll explain this more when we get to it. I'll then tell you about the methods of our work, the actual physical work we do in the lab to search for these phases of matter, and talk about our samples. So this is one device that I made. This is iron telluride selenide. And this device actually gave us most of the interesting data that we got this summer. I'll then tell you about the results we got from those. This is one of the very interesting ones. So this is a graph of differential conductance versus bias voltage. And this new phase of matter will show up as a peak in conductance at zero voltage. So this is a very promising result, and I'll dive into those when we get there. And then I'll conclude with some ideas about how to improve an experiment like this in the future and where we go from here. So, why do we do what we do? The basic idea is that new phases of matter enable new technology. And a simple example of this is water. So if water goes through a phase transition to ice, it can be used for refrigeration. And if it goes through a phase transition to steam, it can be used to power a steam engine. And that's a pretty simple example, but we apply that same idea to quantum computing. And that's one application of the work we do. So this, again, is that quantum computing chip. This was used by IBM in a quantum computer. So what is quantum computing, and why do we care, and how is it different from a classical computer? So a classical computer uses a bit to store information, and that bit can take either values of 0 or 1. There are only two possible values. So a common way to do this is with something like a transistor. It's either on or it's off. There's no in between. It's either 0 or 1. But a quantum computer, on the other hand, uses what's called a qubit, which can take values in between 0 and 1. This uses the principle of quantum superposition. So with these possible states in between 0 and 1, this makes a quantum computer exponentially faster at processing data and can enable things that with a classical computer are impossible, like factoring extremely large numbers. And factoring large numbers may not seem that interesting to you, but a lot of our modern encryption and things like cryptocurrencies run on the idea that nobody can factor really large numbers. And by really large, I mean numbers with like thousands of digits. So for a qubit, you need something in a coherent quantum state. So that would act as your qubit, and it turns out that's exactly what you get in superconductivity. So what is a superconductor, and what properties does a superconductor have? Why do we care? One of them, as I mentioned, is zero electrical resistance. So that red line is the graph of resistance versus temperature for a superconductor. So when you hit the critical temperature, when you're cooling down your superconductor, it starts to display absolutely zero electrical resistance. So this means that if you could when you put a current in a superconducting wire, that current will continue indefinitely with no power loss. But the problem with that is these critical temperatures are extremely cold. So on the order of single digits Kelvin. So we can cool our samples down to 5 Kelvin, which is negative 450 degrees Fahrenheit. So that's really, really cold. And again, a normal conductor, when you cool it down, will display some finite resistance. But the reason that you get no resistance in a superconductor is that the electrons pair up into what's known as a Cooper pair, which is 2 electrons paired together, and all these Cooper pairs are coherent and in the same phase in your superconductor, and can all work together and cause no electrical resistance. So again, that's the coherent state I was talking about for that qubit. The second macroscopic property of a superconductor is what's called the Meissner effect. And this means that when you put a superconductor in an external magnetic field, the superconductor will expel that field. And it does this by inducing currents in the superconductor to cancel that field out. So that's what this is a picture of. When you cool that sample down below its critical temperature and it starts superconducting, it expels external magnetic fields. Now this Meissner effect leads to something called the Doppler effect. And these are those currents that I was talking about that get induced by that magnetic field. So these are two different orientations of a superconductor in a magnetic field. On the left, you have the face of that sample parallel with the direction of the magnetic field. And these red arrows are the direction of that superconducting condensate that's moving around that sample to cancel out that magnetic field. So as you increase the strength of this magnetic field, you increase the momentum of that condensate. And that's a wire coming out the top there. So if you try to have electrons come in here as a current, they need to have the same momentum as those Cooper pairs. So as you increase that magnetic field, it should be harder for you to get a current in here. But on the right side, you have the opposite configuration. So you have a magnetic field perpendicular with the face of that superconductor. And that induces current in loops on the face, like shown there. But if you look at two loops next to each other, those loops cancel out. When one loop's going up, the other loop's going down. That cancels to 0 on the face of that superconductor. So as you increase the magnetic field here, you should see little to no change in the conductance of this sample when you put a wire on it and try to run current through it. Now in addition to the Doppler effect, we see a phenomenon called Andreev reflection. And this is what happens when you try to get an electron from your normal material, like your wire, into your superconducting sample. As I mentioned, there are Cooper pairs in the superconductor. So for an electron to get from your normal material in your wire into your superconductor, it has to be a Cooper pair. So a couple people have touched on bands, but I just want to go over it again to make sure everybody is clear on what's happening here. On the left, you've got your wire, your normal material. On the right is your superconductor. And these are density of states for electrons. So if you have an electron in your normal material that's in the energy gap of your superconductor, it needs to get into a Cooper pair to get in there. So you have this boundary between your normal material and your superconductor. And Z here is how opaque this barrier is. So opaque meaning if it's really opaque, it's hard to get electrons in there. If it's really transparent, it's easy. So as this electron comes into your superconductor, it picks up another electron, forms a Cooper pair, and you get a hole that's reflected on the other side in your normal material. And you can think of a hole as a positively charged electron or the lack of an electron. So this electron moving to the right and the hole moving to the left will give you twice the conductance in the gap. And when you map that out on conductance versus voltage, which is what this graph is, this is your result. So those bottom darker lines are for a really opaque barrier, and you get a dip in conductance, and those top lighter colored lines, if you can see them, that is for a very transparent barrier where you get almost perfect Andreev reflection, giving you a plateau in that gap. So this drives the measurements we do for our samples. So to give you a breakdown of what those samples actually look like, we start with a copper plate, and we put our sample on top of that. I am working specifically with iron telluride selenide, and that goes on top of the plate, and then we add our wires on top, attach those with silver paint, and then apply voltage and current across this. Now this sample goes inside our magnet chamber that's vacuumed out, that we can cool that down from room temperature down to 5 Kelvin, and then we can change the strength of the magnetic field and the orientation of the sample with respect to that magnetic field. So again, working with iron telluride selenide, we have different concentrations of that. The most interesting one so far has been half doped, so equal amounts, almost equal amounts of tellurium and selenium in here, and that's a picture of that device. So the reason we work with iron telluride selenide is there's evidence that this sample will show this new phase of matter. And we put this on a device like this, we attach those wires, and in a perfect world, you get 7 clean contacts. Sometimes that doesn't happen, but that's the goal. And then we test this for that new phase of matter. So, our results. Again, we were looking for that zero bias peak that shows that new phase of matter, and in fact, we did see that. So here's that graph again. At 0 voltage, you get a peak in conductance, and that has to do with how those holes are reflected in Andreev reflection. When you get constructive interference in those holes, you get that peak, and when you get destructive, you get these shoulders coming off the side, and then as you increase your voltage, you start to return to more of a normal metal-type behavior. We also want to see that this peak dies with temperature. So when you warm the sample out of its superconducting state, we want to see that new phase of matter disappear, because we want this to be a product of that superconducting condensate. And in fact, we see that as well. So again, this is differential conductance versus voltage, and each of these colored lines is a temperature. So I have a line there pointing from 14 Kelvin down to the first line that doesn't show a peak, and that is right at the critical temperature of this sample. So that peak starts to die as you warm it up and disappears as it comes out of its superconducting state, and that's exactly what we want to see. And according to that Doppler effect, we also want to see that this peak dies quickly in a parallel field configuration and slowly in a perpendicular one. And it turns out that is the exact opposite of what we see. So this is a plot of the height of that peak as a function of angle with respect to that magnetic field. Each one of these colored lines is a magnetic field value. We went up from 0 Tesla to 8 Tesla. Just to give you an idea, 8 Tesla is 160,000 times the value of the Earth's magnetic field. And that's increasing magnetic field as you go down here. So 8 Tesla is on the bottom. And at 90 degrees, you can see that peak dies. At 0 degrees, the heights are pretty similar, so magnetic field has very little effect on the height of that peak, but it has a really big effect out at 90 degrees. And this is exactly the opposite of what we expected to see. So we didn't see that it died slowly with perpendicular, and we didn't see that it died quickly with parallel. So what does that tell us? And why do we see this kind of field dependence? This is very simple diagram of what might be happening. Our sample, when you zoom in close enough, is not perfectly smooth, and when we put that silver paint over it, that silver paint might be covering different layers of the sample, and when we think the electrons are tunneling downwards into our sample, they actually have access to also go sideways. So maybe that's what's happening, and that could account for that strange result we see. But because we do see that zero bias peak, and we do see it die with temperature, this is pretty promising results and could be evidence for this new phase of matter, which again could be used as a qubit in a superconductor. So promising results, a little bit strange, but we might know why it's going on. And in the future, some possible improvements for this. You could get some cleaner contacts on your sample, and also when we rotate these samples, we have to warm it up every time we rotate, unfortunately, because the system freezes and you can't rotate when it's frozen. So a lot of these field dependence runs take a really long time. So in the future, hopefully we can get that to not freeze and then have a computer program that can take measurements as you rotate. So that would be a huge convenience boost as well as efficiency. We'd be able to take a lot more measurements. So with that, I'd like to thank Professor Birch for allowing me to work in his lab all summer, the entire Birch lab for having great conversations and meetings every week, and supporting me throughout the summer, especially Mason Gray for helping me along the way, teaching me most of what I know about this topic, and always being there when I need him, and funding from NSF for this program, and for Boston College for hosting me. Thanks.
Question?
So you kept talking about this new phase of magic, studying the superconducting field. Is the superconductivity itself the new phase, or does studying reveal some different phase?
So we're looking for that phase in superconducting samples. So superconductivity itself is not the new phase. We know about that, and we know that this exists in these samples, but we're looking for a new phase of matter within that superconducting condensate that I was talking about.
So what is the phase?
You mean like what's the name of it, or it's called a Majorana, but yeah, we're looking for that in these samples. So one way that could present itself is in this peak in conductance at 0 voltage, but there are a couple different things that could show up as that peak. So we need to filter through all this data to see, is that actually what's happening? It's quite difficult to convince people, I have a peak in conductance, I have a new phase of matter. People are a little reluctant to believe you there. So this is good evidence, but there's a lot more work that needs to be done to say that that's what's going on here.
So first of all, thank you for your presentation. I definitely found it interesting and enjoyable. But additionally, I remember seeing like in your further or future directions, you posited that like the surface of the material itself that you're working with is not smooth, and additionally the application of your silver paint can actually have profound effects on the on your results.
Yeah.
And for one thing, I can definitely relate to that. Applying silver paint was definitely a pain.
Yes.
But additionally, have you considered like sanding down your sample to achieve like smoothness more or less?
The level of smoothness we're talking about is pretty minute. So these samples are really thin to begin with. So these steps here are not, I mean, sanding wouldn't give you a perfectly smooth sample. So this is pretty recent, this development, that we finished the measurements on this. So we're still coming up with ways to try to solve this.
So is this focused on a molecular level?
Larger than molecular, but very, very small. So the sample itself, this sample right here, is probably about like 0.1 millimeter thick, maybe. So I have some AFM of it that shows that it's not perfectly smooth, but it'd be quite difficult to get it so smooth and get contacts that are so good that you don't actually have access to like different levels of it. But that's definitely something that needs to be looked at moving forward.
Alright, thank you.
Excuse me. Okay, so at the, maybe the next slide, previous, where, yeah, so here, the B plus and I plus are the same wire?
Yep, on the same wire, yeah.
Okay. So we mentioned you use like, use pro measurement, that you, if you take the I plus and it's a separate context, so that the B plus where you are taking the voltage signal won't have the effect of like, you know, homogeneous current that's mentioned, the current is initially sending in through the sample. You will manage some kind of homogeneity when it's like coming in at that spot. So I think that's the idea why people use the focal instead of to calculate the current voltage in the same spot. So I'm wondering, have you tried to separate your I plus contact?
Yes, yeah, so we did, so with this sample, we're using this 3-wire point contact measurement, but with previous samples, we were using 4, and we changed that to take out the resistance of the junction itself. So that's why we changed the geometry of our voltage and our current.
But if you measure the superconducting state, does the effect of the junction itself is huge in your measurement?
Are you saying like the resistance of that junction?
Yeah, like you mentioned, does that like affect your result quite a bit so that you decide to take that off?
Yes, yeah, yeah, so this, I don't know if you can see, but the top of this, these 3 contacts are all shorted together. So the geometry of these samples and how we apply our contacts kind of dictates how we apply our voltage and our current.
But then why the I plus and B minus is separate?
Why did we choose I plus and B plus? As
Yeah,
the,
like if the junction is going to be an issue, then I would mention I want to combine I minus and B minus issue.
for two contacts, you mean?
Yeah.
I'm not sure why we haven't done that, to be honest with you. Yeah. I can talk to you after that with Dr. Bertram Mason if you want, because I'm not really sure the answer to that myself.
So maybe another quick question, sorry. So I remember in detecting this kind of Marana kind of physics, I think people use STM as a technique as well. But it's looking at the, so as your graph shows, there's this circular thing, like the spot in your graph. You're saying you can put the magnetic field when you see some kind of circle.
Oh, yeah.
So I think if you use that technique, you are detecting that particular signal, which is very localized picture. But if you are doing it, yeah, here. So if you are doing in this kind of transform measurement, it's a much more microscopic than what the other technique is picking up. So I'm wondering, is there a difference between these two type of techniques in terms of determining this kind of thing?
You mean the difference between like these measurements and STM?
Yeah.
I don't know too much about STM myself, so I'm not really sure. But like what exactly are you asking? Like how this measurement measures different things than
Yeah,
STM?
like are they actually getting the same type of information? This one is quite microscopic, the
Right.
other is very microscopic. So I'm wondering, is there a difference between the information you are getting between these two?
Same principle, but I'm not sure what the difference in terms of like the data that you're collecting is. Again, don't know too much about STM,
Yeah,
but I do know that they both of these pretty much run on the same tunneling principle.